We appreciate it very much. And we thank Lucian and the team for inviting us over. It's my second time in Romania.
First time for me.
Brought Rob over for his first time, and yeah, what a beautiful country and city you have, so thank you. The beer's good, so you passed the British test. We're happy with that. So today, I'm just going to give you a brief potted history of Chord Electronics, who they are, what we do, why we do it. It's our take on the industry. Sometimes I might say something about another type of technology that we don't employ. It is not meant in a disrespectful way. It's just meant that they do it this way and we do it that way. So there's plenty of room for everyone in our industry to do what they want. And then I'm going to hand over to Rob. So I'm not an engineer. I'm the sales director. I head up the sales globally for Chord Electronics. Rob's the clever one. He designs all the he does all the digital stuff. So
you know how to talk. It's important.
Yeah, sometimes a little too much. And afterwards, we'd be more than happy to host any questions. We're here for the day. Downstairs, there's a system playing, so we have obviously the headphone systems here, a hi-fi system downstairs, and we'll be mingling about afterwards if you have any questions about anything from hi-fi to rugby and beer. So Chord Electronics was started in 1989 by a gentleman called John Franks. John Franks was actually an aerospace engineer, and he'd been commuting to Hong Kong and back and was just getting frustrated and fed up with that kind of high-level business. He's an aerospace power supply engineer and designer. So he decided to call that a day, and he set up a small business making power amplifiers. Now his frustration was that he was seeing amplifiers that were using a toroid design. Now, as I said, I'm not speaking ill of it, but it's just a fact. A toroid amplifier will amplify the noise that's in the mains. And to negate that, you then need to add power supplies, filters, and all sorts to try and take these problems away. Because of John's history in aviation, the mindset there is design that problem out of it. Don't put a sticky, what would you call a sticky plaster? Like a band-aid.
Bandage.
A bandage over the problem. Design out the problem. So John wanted to use high frequency switch mode power supplies, which in our industry is quite a dirty word because they're very noisy. Now, a high frequency switch mode power supply gives you something that's very important, which is speed and timing, which Rob will go into timing in more detail, but it's critical to what we do. So how do you make a switch mode power supply quiet? So you have the benefits of the speed without the negative aspect of the noise. So he designed a filter system on the front end of the power supply, but also a filter system on the back end of the power supply so it doesn't infect anything else. If anyone here is a vinyl fan or likes more sort of like delicate instrument, it won't affect or harm that signal. So historically, Chord Electronics was actually a pro audio company only. And we started working with the BBC. That was the first contract we ever had. When you start working with the BBC, that instantly opens doors to other studios because they say if it's good enough for the BBC, it's good enough for us. So the next studio we worked with was Abbey Road Studios. And I have to be careful how I phrase this. There are a lot of manufacturers that are able to use a lot of PR about putting a hand up going, we're in Abbey Road Studios. Because Abbey Road Studios is probably the world's most famous recording studio. Studios don't make money anymore out of music. They make money out of promotion. And Abbey Road are able to promote their name and leverage their name by selling space in Abbey Road. So you can put your hand up and say, we're in Abbey Road. So technically you're telling the truth, you are in Abbey Road. Excuse me. We actually power Abbey Road Studios. So when you talk to the engineers, they all use Chord Electronics amplification in the studio engineers. Now we don't have big banners everywhere saying we're in Abbey Road Studios because we're one of the only manufacturers that Abbey Road actually paid for the goods to go in. rather than the manufacturer paying for the goods to go in for the marketing. So for them, their mindset was they absolutely wanted the best, so they paid for Chord Electronics to go in. The negative side of that is we can't have Abbey Road Studios plastered all over our PR and marketing. So, but it's a nice tick for us. From Abbey Road Studios, we went into Air Studios, which is one of the biggest classical recording studios in the world. Sony New York, EMI Japan. We got a call from a lady called Leslie Ann Jones, who was saying she was frustrated because her engineers were complaining that they couldn't work out which amplifier, A, B or C, from other manufacturers. Could we send some equipment for them to try, because she'd heard it whilst recording in London. I said, sure, yeah, where do you want them shipping to? Skywalker Studios in California. So George Lucas now had the whole of Skywalker Studios kitted out with Chord Electronics. So that now means Skywalker Studios, Disney, Pixar. In fact, the new Disney movie that's coming out this year has totally been mastered on Chord Electronics. In the early 90s, John decided to put his technology into consumer products. So the general public, us, we, you, can enjoy the amplification that the studios use. So looking at the amplifier design, what the studios wanted was clean, fast, accurate, and powerful amplifiers. Because even though if we have efficient speakers, you still often need power to get that small signal control, to get the drive unit to move backwards and forwards really, really quickly. So what the power amplifiers do is, like I said, we talk about the switch mode power supply, which is a very clean and fast power supply. It also takes away the need to run a mains filter or a mains conditioner. That actually has a negative impact on a Chord Electronics amplifier. So our recommendation is always mains from the wall, straight into the power amplifier. Let us fix the problem internally. Then it goes through the power rails. The power rails are actually coupled. So instead of an amplifier that's under a lot of stress or a lot of load from some power-hungry music, an amplifier can become slowly unstable. The rails actually shift in parallel to keep the same amount of dynamic power. So there's a lot of dynamic headroom in the Chord Electronics amplifier. We use an awful lot of capacitors. Some people will show a picture with a huge capacitor saying, look, this is really impressive because it's very big. But that has to charge, discharge, recharge, discharge, and that's about speed. So it's a big bucket. It takes a long time to fill. So if you use a lot of military grade caps that are really small, they recharge really, really quickly. So you can keep the pace of music. And why do we use military grade caps? It's very simple. They have a long shelf life. What's made on Monday, Wednesday and Friday is the same. They're reliable. And they very rarely, we've all heard the jokes from military where they say we're working on very, very old technology. It's because the parts are still available. And if you want a product serviced 10, 15 years on, we can still do that. We're looking after amplifiers that we made in the very early 90s. So these amplifiers were a set design that we were obviously tweaking and improving through time. But what Rob will go on to shortly, there's an awful lot about no noise, or incredibly low noise floor. And what's the point in having Rob's technology if our amplifiers make an element of noise which ruins it? It's just pointless. So John was working on a design that was actually started by someone else. He's very open about that. There's a gentleman called Mr. Bell who had a theory about this error correction system. But what John did was he actually took the design theory and developed what we have, which is called dual feed forward error correction. So any amplifier you see that's in our Ultima range has this technology within it. And effectively what it's doing is each stage of the amplifier through a set of signal mirrors, like I said, I'm not technical, so bear with me, and phasing, it looks at the incoming signal and the amplified signal and through a set of phasing controls it can eliminate the noise that each amplification stage makes. So you end up with an incredibly fast, clean signal coming through to your speakers. One of the most common compliments that we get is when people say, what is the sound signature of Chord Electronics? And people can't put a finger on it. It's not too much of this, it's not too much of that, it's just the music. And this is why we are in probably more studios than any other manufacturer. To counter that on the other side, with Rob's technology, yes, we have the engineers working with the amplifiers coming through the studio monitors, coming to the desk. A lot of mastering is now done by headphones. So everything from Mojo through to Dave and M-Scaler is used in the vast majority of studios now for final mastering and engineering, so they can hear the absolute detail of the music and they can work with the artist and get the best possible results for them. Metropolis Studios in London, they master 70% of the UK top 100 album charts, entirely exclusively done through Chord Electronics. There's studio engineers like Glenn Schick who work with a lot of the big American R&B artists, Oscar nominated, Grammy winner. We also work with 9 Inch Nails, Wu-Tang Clan, Prodigy, the list goes on. And recently we were honoured to be contacted by Neil Young. Neil Young does not endorse anything, you know, but he did say he loves actually Mojo and now Mojo 2 so much, he wanted to let us know that he was delighted to use it, and he asked permission if he could put it on his digital newspaper, that he could talk to people about it and say, hey, you want to try this product, this is our favourite product. And we're the only company that's been allowed to put him on our website to say, Neil Young uses this product. So, and here we are today. So in what year was it roughly when you met John?
95, I think.
So the Chord Electronics was growing, doing its thing in the pro world, domestic world, and then in 1995, met this gentleman. I've known you now for 13 years. Travel the world, argue a bit, drink a bit, chat about music and books. But what I really, really respect, like I said, I'm not an engineer. I am absolutely a music fan. I am not a hi-fi fan, I am a music fan. And hi-fi is a means to an end for me. And Chord Electronics is what has given me what I want from the music. And what I love is that when we chat, it's not all about technology, even though Rob obviously has the technical expertise, and I would say genuinely, without a shadow of a doubt, and I don't like blowing you trumpet, so, but number one in his field. But we talk a lot about music, we talk a lot about literature, because these are important, and technology helps you enjoy what the original passion is, and we can't forget that the most important thing out of all of this is the music, and what Chord Electronics is enabling you to do is to get closer to what the artist actually intended to. So at this point, that's a bit about Chord Electronics. I'll let Rob take over and get technical.
I've probably forgotten how to do this since COVID. We used to do it a lot, didn't we?
Yes,
And,
yes, we're very much out of practice.
2 years on, and 2.5 years on, and we've lost the ability to talk to people. Anyway, so my name is Rob Watts. I was always keen on hi-fi as a young lad, as a teenager. I couldn't afford to buy hi-fi, so I started building my own preamps, my own power amps from kits and things. And then I went to university to study electronics, and I studied electronics as a science rather than engineering, because I was interested in the science behind electronics, as well as the practical side of electronics. Always wanted to be involved in audio, in terms of designing. What I'm trying to accomplish is, when you're listening to music, to get emotionally involved with the music. So when you go and listen to an orchestra, it's very easy to get emotional with music. your spine will tingle. If you're listening to rock music, your feet will tap. Getting emotionally engaged is the key of what I'm trying to do. I'm also trying to make it so that when you're listening to poorly recorded music, you get the maximum benefit you can from that particular music. And this is actually strange because since going up to 2015, as I made improvements to my DACs, what tended to happen was the best recordings got better, the worst recordings got worse. And I thought, well, that's obvious because you're hearing how bad recordings actually are. And then something changed in 2015. The big change was with Hugo. Hugo was a dramatic change in technical performance because I suddenly had FPGAs. And FPGAs are programmable gates that you can create your own digital circuit. So it's like creating your own chip. You can do what you like, and it's low cost, relatively low cost, and you can do whatever you want to do. But in the past, I was always limited in being able to do things with the digital side. I wanted better filters, I wanted to be able to do better noise shapers, and I could just squeeze in what I could do to suit with the size of the FPGA. Suddenly, in 2015, we had much better FPGAs, 3 or 4 times more capacity, much lower power dissipation, so we could do portable products. But anyway, I suddenly had an FPGA where I could do lots of improvements I've been doing in the past and things I wanted to do. Plugged that into Hugo 1, and I was pretty amazed because not only did my good quality recordings get much better, strangely, the poor quality recordings got much better, and even better by a bigger factor. And I found that I was now enjoying music that before I didn't enjoy. So piano music. Before Hugo, didn't like piano music because it just sounded boring. Suddenly, after Hugo, you could hear what the pianist was doing, the timbre, the way he was attacking the keys, the way the music flowed, and it just suddenly sounded much more natural and much more enjoyable. And even 1930s mono recordings, which in the past I wouldn't touch with a barge pole, suddenly you could hear all the distortion and noise and everything else, but you could perceive the music as well. You could hear what was good about the recording. And that changed things dramatically for me because it meant that instead of 0.1% of my recordings I could get musical involvement with, it was now more like 50% of my recordings I could get musical involvement with. So how is it that suddenly getting more musically involved became a feature, became a benefit? What was it that I was doing that enhanced my musical enjoyment? And it comes down to 3 broad things that are important. And these things are issues that no other digital designer talks about. And the first issue is small signal integrity or small signal accuracy. The second issue is something called noise floor modulation. And the third issue, which is the most important issue, is about transient reconstruction and how accurate the timing of transients are. So small signal accuracy, what are we talking about here? So small signal accuracy, when you have a digital signal and you put it into a DAC, if you've got a signal set to 0 dB and then put in a signal at say minus 100 dB, which you would not be able to hear, it's so small. If you measure the amplitude coming out of the DAC, it's not going to be minus 100 dB. So in the early days, when I was first developing DACs in the 90s, you'd be looking at 1 or 2 dBs worth of error. So you'll be looking at 98 dB coming out rather than 100, or say minus 102 dB. As time went by, with pulse array, for example, that issue was eliminated in that you could measure minus 100 dB and it will come out exactly at minus 100 dB. In fact, my threshold of testing when I got better test equipment, is I could put in a signal at minus 120 dB, and it would be accurate within a thousandth of a dB. You have to do the measurements for about 3 or 4 hours to be able to get this level of accuracy. So it takes a long time to do the measurements. So I knew when I improved the small signal accuracy, you got better detail resolution, you got better depth. Depth is a real key problem for me, because when I listen to an organ in a cathedral and you shut your eyes and the organ is 100 meters away, when you listen to it, it sounds exactly 100 meters away. And if it's 50 meters away, you can tell the difference in depth. But when you play that back through headphones or loudspeakers, it'll sound like it's a couple of meters away. It won't sound like it's 100 meters away. So depth is something that has always been a key problem for me. And I found that as you improved the small signal amplitude accuracy, you got better perception of depth. Going back to Hugo 1, and when Hugo 1 was finished and then I started developing Dave, one of the interesting things I found with Dave was that I had an even bigger FPGA. And I thought, let's try making better noise shapers. Noise shaper is an essential part of a DAC. And if you want to know how a noise shaper works, then talk to me afterwards, because it's a bit complicated. Anyway, they're an essential part of a DAC. And you can measure performance of a noise shaper. You do something called a digital simulation, and you can extract the numbers digitally, and it will tell you exactly how well that noise shaper is performing. Hugo 1 level, I used to work to a performance of 200 dB. So that's 32-bit accuracy, and it means that if you do a signal noise measurement of a signal, it will be accurate to within 200 dB. You ask a digital chip designer and say 200 dB's performance for your noise shaper, they'd say, you're crazy. You don't need that level of performance. And in fact, chip manufacturers generally work to 140 dB accuracy, because they say, well, the noise is at 120 dB. Why do you need accuracy better than 120 dB when you only need to work to 140 dB? So I was working at 200 dB, and if you'd asked me in 2015, is 200 dB good enough? I'd say, yeah, I think so, why not? It's a really good number. But then with Dave, I had the ability of having better noise shapers, 20 elements, and I tried listening tests. The thing about audio is or designers, always make an assumption about something making a difference to the sound. It's a good enough level of performance. Most people give up and stop, but they got to a good enough level of performance that they leave it alone. I don't do that. I always question things. And so I thought, let's try a better noise shaper. Ran to 220 dB. Did a listening test. Pretty gobsmacked. Depth got better. And this was really bizarre, because I thought, hang on, how can something at 220 dB sound better than 200 dB? Because that's just silly numbers. So I thought, don't really care, because all I want is better depth. So let's keep going until it stops improving the sound. And over a 3-month period when I was developing Dave, I kept on improving the performance of the noise shaper. 240, 260, 280, 300 dB. Getting to 300 dB was really difficult. And then I managed to get to 330 dB. And each time I improved it, it was a great experience, because I'd get up in the morning, I'd think about what I did the previous day, think about ways of improving things, start writing some code, do a quick simulation. By the afternoon, I'd improve the noise shaper, and then doing a listening test, bang, it's better again. And then the next day, the process would start over again. And eventually, I hit 350 dB. Going from 330 to 350 dB was the first time when it started to become a struggle to hear the difference in terms of depth. So that sounded like we're pretty much, at the end of the cycle in terms of improvement. So small signal accuracy is vitally important to your perception of depth and detail resolution. Don't ask me why we need 350 dB performance figures, because that is just a crazy, crazy number. There's no way we can hear minus 350 dB. And you could argue, well, it's not about minus 350, it's about your accuracy of minus 100 dB. But even then, when you look at the numbers, it's 10 zeros, 1 dB error. It just makes no sense to me that we can hear these things. But we can. I'll tell you a little story because this is pertinent to this. Because a lot of designers say, or people attacking me say that I'm making these numbers up because it makes no sense. And I agree with them, it makes no sense that these numbers are important. I used to design silicon chips for large silicon companies. I spent 15 years designing silicon chips, creating IP, patenting the IP, and then selling that IP to chip designers. So I've had a broad experience of designing silicon devices. One of the companies that paid me multi-million dollars for my IP, they wanted to acquire my IP, they were paying a lot of money for it, and what they wanted to do was to embed the IP in the company, so that after 3 years they could say, bye-bye, go away, and we can just develop your technology, which I was quite happy with because I don't really like working for large companies. I like doing what I want to do. So it suited me, but I spent a lot of time talking with their engineers. Now their engineers are very smart people, actually more intelligent and more capable than I am. And I learned a lot from them. But every time we had these arguments, and I'd say, we need to do it this way because it sounds better. And these are the numbers, and we need to stick to those numbers. And they would say, you can't possibly say that these numbers are important. In that case, going back there, I was talking about 200 dB performance noise shapers, which was costly to do a 200 dB noise shaper because you have to use quite a lot larger number of gates than you would otherwise normally use. So for 2 or 3 years, we had these arguments, and I can constantly go ahead and say, you need to do it because it sounds better. So eventually I invited one of their engineers over to my house. And I had a noise shaper set up. One was set to 180 dB performance, which is perfectly good enough. Another was set to 200 dB noise shaper performance. And I said to him, listen to it, and see if you can hear a difference. So he did it backwards and forwards. And he said, you know what, Rob, what surprises me about this, after he'd heard the changes, what surprises me about this is not that you can hear the difference, because I believed you. I spent a lot of time believing you. What surprised me about this difference from 180 to 200 dB was how big it was, and how easy it was to hear the difference. And he wasn't an audiophile, he was just an apps engineer, and he wasn't an audiophile. So he then wrote a report back to the company. Then after that, I got no bullshit about you need to do it this because it works that way. There was no longer any arguments. So these things are real. And when I get to a situation where I have a very small number that makes no sense to me, what I normally do is do a blind listening test with my son, just to confirm that it makes sense, that I'm not imagining the changes in sound quality. And he's always confirmed what my things were. So we've talked about small signal accuracy. Next thing that's really important is noise floor modulation. Noise floor modulation is very important because it affects your perception of timbre. We were talking earlier about musicality, being emotionally involved with the music. How do we technically create a DAC that allows you to become emotionally involved with the music? And the key factor is variation. And variation is very, very important. So if you have a DAC has limited variation, then you won't get emotional. And variation, we can be talking about variation in space, variation in timbre, so having a bright instrument and a dark instrument, playing those together at the same time and being able to hear a bright trumpet against a rich sounding saxophone. That variation is very important. Variation in dynamic, variation in starting and stopping of notes. All these things are critically important. The other problem you've got is when you're doing a listening test, how do you know what you're listening to? You've got a recording. You weren't there present when you were doing the recording. You didn't hear the original acoustic, the original music that was being played. You don't know the sound of the microphones, you don't know the sound of the cables, you don't know the sound of the mixing desk, you don't know the processing that the engineer is doing. You have no idea what that recording actually is. So when you're doing a listening test, is it because you're getting an improvement because it happens to work a little better in your system with that particular recording? You're just optimizing the sound of your system, or are you making a fundamental improvement? And the only way of finding out whether you're making a fundamental improvement is to ask the question, is this sounding more varied? Am I getting more variations in depth, more variation in timbre, more variations in dynamic, and being able to perceive starting and stopping of notes? If you get more variations, you know you're fundamentally making an improvement. You're not actually just changing the sound to suit your taste. So, going back to noise floor modulation, this affects your perception of timbre. And what happens is that when you measure a DAC, if you measure the signal with a very small signal, you'll get a noise floor that's like that. So typically you'll be looking at minus 160 dB noise floor when you're doing your measurements for a minus 60 dB signal. Problem is with conventional DACs, if you then increase the level, the noise goes up. And the noise goes up in sympathy with your signal. So the noise pumps up and down with the signal level. What we want to do is to have a static noise, so when the signal goes up and down, the noise stays the same. And this is very important subjectively, because if you have noise that pumps up and down with the signal, the brain cannot tell the difference between the sound of the noise and the sound of the instrument, because they're coupled together. So when the brain is processing things, you're separating out individual sounds. The brain is doing that work, it's not your ears, the brain is calculating what's going on. So if you have a saxophone that's got a white noise pumping up and down with it, that saxophone will become brighter because it's got this noise pumping around. If there's another instrument playing at the same time, then you've got noise that is from the saxophone and from the other instrument, and then the brain gets confused because it can't tell, well, is this noise the sound of the saxophone, or is this noise the sound of the other instrument? And then you get a blurring between one instrument and another instrument because the brain can't extract the information to tell whether it's noise that's separate or whether it's noise that's part of the saxophone or noise that's part of the other instrument. So your instrument separation and focus gets degraded. And instrument separation and focus is when you have a big instrument, another instrument playing that's quiet, and being able to hear that quiet instrument when the big instrument comes in and out. And that again is very, very important when you're trying to get emotional with music. So noise floor modulation is a key quality with chord DACs. And you can do careful measurements, and I can show that all of the DACs from a Mojo 2 up to a Dave have no measurable noise floor modulation. All other DACs that are available will have measurable noise floor modulation. But the story gets more complicated than this, because I've actually asked the question, what level of noise floor modulation is important subjectively? And the answer to that is, it doesn't matter how small the noise floor modulation is, somehow it interferes with the brain's ability to separate individual instruments out. So you can have noise floor at minus 350 dB changes at minus 350 dB, and that affects your ability to separate individual instruments out and your ability to perceive the timbre. So basically, the smallest amount of noise floor modulation would be impossible to measure, apart from when you're doing digital simulation, because I can measure it with digital simulation. But if you're doing real measurements with real test equipment, you'll never measure it, are still audible. And that brings me back to what I was saying earlier about small signal accuracy. If you've got the smallest error, somehow the brain detects it when it's processing it, and that interferes with your ability to perceive things properly. So the final thing, and this is probably the most important one, is transient reconstruction. Now, the problem we have with digital, and this is a unique problem with digital which we don't tend to have with analog so much, is, sorry about that, I should have turned my phone off. The problem we have with digital is that it's sampled data. So we have one sample, and then 22 microseconds later, we have another sample. Analog, of course, it's a continuous waveform, so we don't need to worry about what's happening from one sample to the next sample. We know from psychoacoustics that transients are very, very important from a perception point of view. So transients are used to work out timbre, for example. So you can take a transient, if you remove the transient information of a sound of a piano and a trumpet. They've done these psychoacoustic tests where they've removed the transient information. It becomes very difficult to tell the difference between the sound of a piano and the sound of a trumpet. So transients are very important for the perception of timbre. Transients are also used for location, left to right. And we know that the two ears, there's something called the interaural delay. The brain measures the timing difference between the left ear and the right ear. If you go to conventional textbooks, they'll say we can perceive something like 4 microseconds worth of delay. Recent research has shown that actually 4 microseconds worth of delay is not the accurate number, that actually there's no resolution limit. So we can hear any difference, or the brain can use any difference in timing between the left ear and the right ear. So that's recent research that was published a few years back. And they did this by cutting up gerbils and finding out different velocities of transmission within the cellular structure. Anyway, that's rather gruesome if you read the paper. So we now know that the brain is working to virtually infinite resolution in terms of timing. So timing is very, very important. The problem we've got with digital, of course, is that the transient information is being lost in that we've got one sample here and one sample here. We don't know what's going on between the two individual samples. Sampling theory comes back to help us on this, because we know that if you go into the original theory, into the original mathematics, we can perfectly reconstruct the information, or rather the waveform, from the first sample to the next sample. This is how sampling theory is proven. Trouble is, to perfectly reconstruct, you have to do something called a sinc function. And a sinc function means an infinite amount of processing. You have to go into the infinite past and the infinite future and work out what's going on with the signal, and then you can calculate exactly what it should be between the two. I knew way back in the 1980s, when I first heard digital and it sounded so terrible, my vinyl was so much better, I knew that this was a fundamental problem because I studied sampling theory. I also studied about psychoacoustics and knew that transients were really important, and I realized that the problem we've got with digital is the reconstruction of the timing information from one sample to the next sample. And this was a fundamental problem. And I worked out, in those days we were talking about 16-bit digital audio, I'd worked out that if we wanted to reconstruct it to within a 16-bit accuracy, we would need more than 500,000 taps to do this. 500,000 taps is an enormous amount of processing. Going back to the 1980s, when digital filters didn't actually exist, you used to use analog filters. The idea of 1,000,000 taps was just like going to Alpha Centauri and back in the same day. It was just impossible. And we'd never be able to do this. But anyway, the good thing is that technology improved, and come the 1990s, I had FPGAs that could do a decent amount of processing. And in those days, it was 1,000 taps. The kind of filters you could buy off the shelf that I had to use, you're only looking at 128 taps. A tap gives you a measure of how much processing power is involved in the filter. A sync function, to reconstruct it perfectly, would need an infinite amount of taps. So you need to do an infinite amount of processing. So 1,000 taps was a 10-fold improvement on what you could do with that. Listen to that, and lo and behold, it sounded a lot better. It sounded better in the ways that theory would predict about transients. So you could, one of the things I didn't mention was that bass performance depends upon transients. So we perceive pitch of a bass guitar from the transient which you're plucking the string. So if you lose the transient information of bass, it becomes difficult to follow the tune. So when I went from standard filter to 1,000 taps, you could hear a big improvement in pitch of bass. You could hear the timbre variations being better. You could hear the starting and stopping of notes being more accurate, which of course you'd expect, because starting and stopping of notes is all about transients. So then I thought, well, hang on, 1,000 taps is nothing like 16-bit accuracy, for which we need 1,000,000, and that in the 1990s that was still impossible. So I thought, well, is there a way of changing the algorithm? The algorithm is the thing that you use to calculate where you are in terms of the coefficients, how you change the filter. In the past, what you use mathematical algorithms to do it. So you'd use a Kaiser function, or you use a different windowing function. These are standard things that mathematic people employ. I wanted to create my own algorithm that was optimized to improve transients and reconstruction. So I went ahead, tried different things, did lots of listening tests, and in the case of the WT algorithm, that has been fine-tuned over the past 25 years with thousands of listening tests, because I've ended up with a formula with 5 different functions on it, and you have to listen to each individual function, fine-tune it, adjust the variable, listen to it, adjust it again, listen to it, and listen to all the various things that we know that transients are important, like pitch, like depth, like instrument separation and focus, like timbre variation. Score those things, and then go to the next variable and tweak that. And so it was literally thousands of listening tests to optimize this filter design. Nobody else does that kind of thing, because they'll use an existing math, bang, use it, forget about it. Say it sounds wonderful because I've designed it, it's wonderful, and it's coming from this wonderful company, which everybody knows has got a big brand, and that's the end of it. So nobody does this kind of craziness in terms of listening. Now, of course, as time has gone by, we've had more capacity in FPGAs. With the M scaler, we're looking at 1,000,000 taps, which now means I can guarantee that when you go from one sample to the next sample, we will reconstruct the waveform to a 16-bit accuracy, because that's what the maths tells you, and that's what I've got. Question now is 16-bit good enough? How do we know what level of performance that we need that's good enough for the brain? Because it's It's not about the numbers, because 16-bit happened to be 16-bit because that was the level of performance that we need. The work that I've been doing over the last 5 years is exploring how many taps do we need to improve the sound quality, what are the limits that we can in order of getting this. One of the things that I've been working on is my own A to D converter. And that's because one of the limitations we have with recordings is the quality of the A to D. You know, we're talking about small signal accuracy, we're talking about noise floor modulation, we're talking about transient reconstruction. These issues are exactly the same issues in A to D converters as they are in DACs. In fact, you can actually say a DAC is the same as an A to D, except with DACs they're digital integrators, with A to Ds they're analog integrators. So they're pretty much, mathematically, pretty much the same kind of thing. So they've got the same issues. Beauty of this is that I can record at 768 kilohertz, will be able to record at 768 kilohertz, decimate it down to 48 kilohertz, listen to it, bring it back up to 768 kilohertz and find out what the total losses is. So we'll know for certain how much this is a problem in real life. And that's something that's ongoing. In fact, I'll be testing the A to D converter in a couple of weeks' time. So I'm pretty excited about that. The other thing I've been doing is doing my own recordings, using Blumlin ribbon microphones, and one A to D converter, no post-processing, no editing, keeping it as simple and as direct as possible. So that means that when I replace the Pro A to D converter that I'm using with my own A to D converter, I'll have complete control from the microphone to the headphones. And I'll be able to compare what I get on the recording against the live sound that I've heard. And this is really powerful. And in fact, it's already shown certain things that I already suspected of deficiency problems with it. But that's something that's ongoing, and that's going to be a lot more progress in the future. So I think I've pretty much covered everything. Please ask some questions, because the best thing about these kind of events is people asking left field questions, or even what you think is silly questions, because the silly questions are actually often the best ones to answer. So please ask some questions, and then once we finish this, you can come back to me and talk in more detail, and we can go downstairs and have a listen to what I've been talking about and see whether it actually works for you. So please, some questions.
I have a question.
Sure.
Since you produce some of the best DACs in the world, why did you produce also streamers?
Okay, so streamers are an interesting thing. And this question was asked to me yesterday. Why don't you do a chord streamer? Well, my job as a DAC designer is what I'm interested in doing. And I do projects that I want to do. So I'm not into doing a project because it's going to make me more money. So I've made enough money, I don't care about that. I do things that I want to do. And that, you know, I don't get up at 3 o'clock in the morning and start working and work 7 days a week because it's something to make a little bit more money. That's not relevant. I'm doing it because I want to enjoy my music more, or to understand how to enjoy music more. One of the two reasons for doing that. My things about DACs is that if you're feeding it bit perfect data, any source should sound identical, whether you're using a mobile phone, whether you're using a PC, or whether you're using an audiophile streamer. They should all sound the same. Currently with my DACs, they do not sound the same. We'll have different streamers sounding different, and there are various technical reasons why that is the case. My job is to make it so that it doesn't matter what you're using, and I've isolated the issues that are involved in all this, and I'm busy trying to improve the DAC so that we can have it so that it's completely independent of the source. It doesn't matter what source you use, it will sound the same. That to me is the better focus of my time, if I were to get involved in streamers, there's a whole host of things that I have no expertise in. And I'll be learning things which actually is not going to improve performance, because focusing on the DAC and making it so that the DAC is not sensitive to the noise that's coming from the streamer, that's the key issue. Now, no doubt in the future, Chord will hire other consultants and other engineers and develop their streamers and develop streamers that all work with my DACs. And that's something that
One thing we certainly won't
Colin can
do,
talk about.
I mean, just in short, one thing we won't do is do an integrated stream DAC, because A, it's not what Rob wants. Commercially, it's not what I want. Commercially, I can probably guarantee it's not what this gentleman wants, because we do basic Mojo level, Qtist level, TT level, Dave level. Which one would you want? Well, you may wish a Dave, you may wish Qtist, you may wish a Mojo. This poor gentleman I have to manufacture 4 or 5 different levels. This gentleman has to stock many, many more products. So if we have a streaming platform that we're working on, the biggest problem, the most expensive problem is software. So if we do release a streamer, it will be like a bridge, network bridge. And then you can choose which DAC you choose to feed it into.
And it's important that the streamer is separate from
Yes.
the DAC, because any noise from the processing is a complete nightmare in terms of sound quality and performance. So the slightest amount of RF noise, and I'm talking about nanovolts worth of noise that gets into the DAC, will degrade the performance, the sound quality performance. So if you can keep it separate, you've got a much better chance of containing that noise and preventing it from getting inside the DAC.
Okay, regarding the streamers, you have already one streamer to go, and from some time the Apple iOS application is still crashing. Do you know?
Yes.
And I know that you outsource the software part to another company,
Yeah.
but the software is not at the level of your hardware.
I understand. So, hands up. Yes, it's not good enough. So the original concept of the software behind Poly and To Go was, because I worked in retail. I've spent many years in retail, and one of the frustrations for me as a retailer when selling streaming product is often it's not necessarily the performance of the streamer that sells the product, it's the performance of the software. So for example, if you look at Sonos, a Sonos device, the software is excellent, but the performance is not as good as you could get if you use, say, Rob's DAC. So I'm not going to speak ill of Sonos. So there's this, which do you go down the route of? Now, we decided not to do control software because of software packages such as Room, many other DLNA, UPnP software, and our assumption was that you all would say, well, I don't need to have a Chord Electronics software package.
Yes.
I would use a third-party one that's more specialised.
Yes, I use Root.
Yes. So for some people it's not acceptable. So I can safely say iOS 16 was fine. Apple send us the test software so we can prepare the software to run alongside it. When they release their software, it's not the test software that we had. So,
I know.
which is brilliant.
I know.
But we're working
I
on
must borrow an Android device to update the firmware.
Yeah. So I can safely say we're working really hard. There was actually a meeting Friday and
I'm
another
in
one
the
Monday.
branch, I know. It's,
Yeah.
if you are aware, you'll fix it.
Yeah.
Like Hegel with already 3 years, but it will be fixed in
Yeah.
the final.
Yeah.
And I have more questions for now.
Sure.
Yes. First, about how Chord Dave treat and the M scalar read the information from MQA files. I'm not
Oh,
a fan.
okay.
I'm not a fan, but for me, MQA information in non-MQA DAC, it's only unwanted noise.
Yes, yeah. So the problem with the MQA process is that it degrades transients. You've got very limited amount of taps. You've got aliasing problems. I mean, when people have done measurements on the MQA process, we're looking at 1% distortion above 20 kilohertz. That is completely unacceptable. And that level of aliasing will degrade the performance. So we're at complete opposite ends of the spectrum in terms of what is needed to do. Now they say the aliasing has no issue. They actually haven't done any listening tests to show.
We have.
Yeah. They don't talk about transients and the importance of transient reconstruction. You cannot do what they're doing without degrading the quality of transients.
Yes, but
So some people have said, and I listened to when the MQA first came out. I listened to the filters when they first came out to us, and we managed to connect it directly through to the DAC, and we can hear enormous degradations from their interpolation filters. So we had wanted nothing to do with it. It was actually quite challenging at the time because when it first came out, there was such a big buzz about MQA, and we were saying no, we're not doing it, and a lot of customers would not buy our DACs because we took that stand. Unfortunately, Chord backed me on this approach.
yes, but I am.
But going back to your question, sorry,
Yes,
I'm dragging on a
okay.
bit. You can of course decode the MQA through your software,
Yes.
so that's doable. I have seen reports. I haven't tried it myself. I have seen reports that some people prefer the sound without decoding it, and listen to your MQA file at 44.1 or 48 kilohertz. Listen to it directly, and that sounds better. Perhaps that's a better way of.
What is happening in your DAC with the MQA information? Because on Tidal now, all the music is MQA encoded and remove the flag.
Yeah. So my advice is don't use Tidal.
That's why I switched to Converse, but it's not commercial and
Just don't use Tidal.
Okay, so will be distortion, this
There will
information
be.
in your DAC.
You're limited by aliasing distortion. 1% distortion is complete. If I produced an amplifier that had 1% high frequency distortion, stereophile would shit on me because that's just completely unacceptable. But when it comes from Bob Stewart and MQA, they say it's perfectly okay. They're idiots.
Can I give you
It's crazy.
No,
1%
for
distortion.
me, it's what I listen, I like, it's okay, it doesn't matter how
No,
much.
that's, yeah. The reason some people like the sound of MQA
Oh, I know.
is when you remove the transients information, you can't perceive pitch properly. So what happens to your bass? Your bass sounds fat and
Yes.
flabby
I-
and lacking tunefulness. But that big bloom of bass, some people like that sound.
I
You know,
put,
So, and if,
I make a test with Dave and DCS rerun on MQA files. And really on MQA, DCS wins.
Yeah, because we're not. I'll give you a small. I'll give you a
on
small quote.
non-MQA, Dave wins.
yeah.
There was an interesting statement I briefly touched on earlier that Neil Young endorses what we do, and a lot of people will be, I think, unfairly cruel to Neil Young because of his Pono project. The Pono project was purely a portable device that he could take to the car manufacturers because he wanted everyone to get a better experience in car audio, not just by fixing the speakers, by fixing the front end. And he actually had he discovered that large corporations don't treat people very fairly, and I won't say who they were. You can read his book, Waging Heavy Peace, it's a fantastic read. But when he talked to Neil Young about it, he pulled off of Tidal because they released the MQA masters.
I know.
They messed with his music, and if we take away the technical side of MQA, which we all listen to and we all agree on, how can someone rightly and justly go to an artist and say, I'm changing your music and I'm selling it as your music when it's not your music? And the quote from Neil Young was, those are not my masters, I'm not going to allow you to release them. So
Okay. Did you know that I found the NQA files even on Kabul? So it's a plague. It's spreading. Another question
Sure.
is about DX links in your product.
Sorry, the
DX.
DX, yeah.
What is about this?
Oh, okay, so the DX program was, imagine you've got a DAC. The benefit of my DACs is that the analog section is very, very simple. The digital is very, very complicated.
Yes.
And this is what's strange about digital audio. Analog always sounds better when it's simple. People that then apply that idea to digital and say, well, the best digital is simple, that's completely wrong. The most accurate sound is when you have really simple analog and really complicated digital. That's how you get the accuracy. So my DACs are very simple. One amplifier, that's all there is. 2 resistors, 2 capacitors, connecting straight to your headphones. So you get a very short path from the digital domain to the analog because it's very short. What I wanted to do, or what I intend to do, is to have, at the moment with TT2, we've got 7 watts of output into 8 ohms. I want to have DACs that can do 100 watts, 200 watts, 400 watts. Again, digital input, 1 amplifier, and that way we'll get much better transparency. So the DX outputs are for future DACs that are powerful enough to drive big, inefficient loudspeakers directly.
Okay.
So it's a future program. It's kind of been stuck because
It's a digital amplifier,
It's-
not class D.
it's
I'm also
it's not plastic.
electronic.
Yeah.
It's
So
not-
it's
a digital.
it's to go to other DACs that don't have volume controls, that will have enough power to feed out.
So
loudspeakers
now
directly.
what output I have on my DX?
no,
So
ignore it.
ignore it.
Ignore it. It's
Until-
not.
So if I put an oscilloscope, what?
You can connect another Dave to it. In fact, I to test it out, I had 2 Daves, and you use the DX outputs, and they would actually sound better because the second Dave is not doing any WTA processing. It's not something we talked about because I didn't want to encourage people to sell 2 Daves. Japan are busy selling.
Because
Japan are busy doing
another
that.
issue, you put you lock the FPGA to not update, to not
Yeah.
copy
So-
the.
So there's a number of different reasons for this.
Yes, I know.
the-
So you must change the board to get an update.
The first reason is we don't have the capabilities of doing the updates originally, and in going back 2015 it would have been impossible. Today it's technically possible, but we'd have to change things. But there's a number of different reasons for it. Firstly, the primary reason is that when I do a design, I optimize the FPGA code. I optimize it with the hardware. You're limited by the hardware. You're limited by the size of the FPGA. And I do the best that I can. So with Dave, it took 2.5, 3 years worth of development. Once that project was finished, I'm done with that. I move on to something else. We've got so many other things to do. I'm not like some designers that only have one product to look after.
Yes,
There's a
yes,
lot-
audio.
Yeah.
To change the sound on every.
Yeah, and that to me is a big problem, because what the hell are you listening to when you go into a shop? Which update have you got? Is it the brighter one, or the warmer one, or the softer one, or the darker one, or the you know?
The purple patch.
Yeah, and you put something in for review. What are you buying
And
so that to me is not the right way forward.
if you unlock the FPGA in 1 month, you will have Chinese deals.
Can I just say we've got a question here. Sorry, 1 second. What we'll do is we'll take this last question, and then we're here for music. So if everyone then like to make their way around.
I have one.
No, bear with me 1 second.
Okay.
So we'll take this question.
Yeah.
Then everyone can go and listen to some music, and then if you wish to take it in more detail, we'll take
Talk
your
to
side
me.
and we'll do it separately, so everyone can enjoy the actual music from the system. So your question, sir.
Yeah, so hopefully the question will be of interest to all of us. Building on the first question that was asked here, so if you are, first of all, how do you make sure that the source is bit perfect? And building on this question,
Okay.
a bit more personal, what do you use as a digital source?
Right. So making sure it's bit perfect.
Yeah.
The best way is use a DSD file. Set it to DOP, transmit DOP. If it's not bit perfect, it won't get through and decode the DAC. So that's the easy way of checking for it. Of course, most software like JRiver, for example, Room will tell you it's bit perfect. The data is the same. You can trust that statement. But if you're worried about it, use a DSD file and check that it converts it to DSD. And
We're not recommending you listen to DSD.
No, that's another conversation.
Yeah.
That's another conversation.
Okay.
And what was just?
Was a bit more personal. Like
Oh,
what
what
do you
source?
use as a
What source do I use?
Or streamer or transfer?
So I don't use streamers. For mobile use when I'm on a plane, which is a lot of my listening because I spend about 300 hours a year on planes.
It's an iPhone.
I just use my mobile phone. So there's 1 terabyte worth of music on this. And the beauty of mobile phones is USB out straight into the DAC. If the DAC is battery powered, the source is battery powered, you've got perfect isolation. There's no way there's going to be any current flowing, so you're going to get the best sound from that situation. When I'm at home, going back a few years ago, I had an MSI laptop, which was my main design laptop, and on that I could use an optical output and I had a USB output. I'm going into Dave, or actually going into the M-Scaler at the time, and then into Dave. You couldn't hear a difference between the optical and the USB, and I used USB all the time because it was as good as optical. But I upgraded into an enormous performance computer that my son built for me a couple of years ago. This had an 800 watt power supply, it had 64 gig, it was the fastest processor you could get. That was also an MSI motherboard that had optical out and of course the USB output. Connecting that to my M-Scaler, you could hear a difference in that the USB sounded worse, significantly worse compared to the optical. So optical is your reference, and what you're trying to do is to get the sound quality to be as good as optical, because there's no possibility of currents flowing into the DAC and then corrupting the DAC. But some sources, the optical sounds as good as, or the USB sounds as good as optical. Other sources, USB is inferior. It doesn't really matter what the source is, but use optical as your reference to see if what kind of sound quality you're getting.
Right, but to zoom on the question, how do we make sure that the samples we're getting from this digital source are actually, one-to-one bit perfect, and that there is no change in software?
I know they're bit perfect because of measurements that I do. So some of the measurements that I do when I'm doing a place, and in the old days, used to do something called a place and route on the FPGA. So you've got your design, you've got your coding, you want to create something that will work on the FPGA. And sometimes it would fall over because the tools weren't very good. So what I used to do is to plug it in with optical going into the unit, using the audio precision, run it for an afternoon and use it for thousands of averages. If one sample has got an error, it will completely screw up your FFT, and you'll see it. So you can run it with optical for 4 hours and know that there's not a problem. The DAC has been busy warming up, and going from cold to warm, you would then identify whether there's issues with the place and route. I still do that because that's just part of what I do, and I've enhanced that technique. I no longer need to do that from the place and route point of view because the software tools are absolutely really good today. 7 years ago from Xilinx, they were terrible. You had to, each individual place and route sounded different. You had to check that it actually worked correctly. We don't have those issues today. But making sure it's bit perfect, you know when you're doing measurements. Because if one bit falls out, you see a huge error, and it's easy to see.
All right. Thanks
But for yourself,
Yeah.
just use DSD. If it turns
I'll
into
try that.
DSD, you know it's bit perfect.
Thanks a lot for your answer, Rob.
Okay,
So
thank
I
you.
guess it's time for music.
Yeah,
Yeah,
I mean,
thank you. Haideți să mergem jos. Cine vrea, nu